The prelim exam in analysis at University of Pittsburgh usually has some interesting questions, and today we're looking at one of them. Suppose you have a continuous function from Rn to Rn, same dimensions, but that's insignificant, I believe, and let E be a compact subset in the domain. Suppose that phi satisfies these two conditions. First of all, it's one-to-one on the set E. That's a global condition. Number two, at every x in E, there is some radius so that phi on the whole disk around that point with radius Rx is one-to-one. This condition, notice that it goes beyond E, so it's everywhere on this ball and not just restriction of the ball to the set E. Under these two conditions, prove that there is an open neighborhood of the set E on which phi is one-to-one. So this one is also a global condition, and that is actually the subtlety behind this question. Whenever you are given a problem to solve or something to prove, the first question is always, oh, isn't that obvious, or what makes it not trivial? So here's the point. So you have the set E, and you know that at every point there is this tiny ball on which it is one-to-one. So why don't you just stitch together all these balls and form that open neighborhood, U? Well, the problem is if you have some x here and some y here, nothing stops you a priori or in an obvious way from having this condition, even though x is other than y. So if both x and y are in the set E, that follows from condition I. But what if one of them or both of them is in U minus the set E? And that is exactly the point of this claim, that despite this apparent lack of control, we do actually have such an open neighborhood. Maybe it's not this union of balls, but something smaller. I'm going to give a proof of this, but unfortunately it's a proof via proof by contradiction. I have nothing philosophically against proof by contradiction, but I would love to see a constructive proof which also tells you how to come up with this neighborhood, or what does it depend on, or how big can we choose it, depending on the shape or geometry of the set E, on the uniform continuity constants of the restriction of phi to the set E. I believe there has to be some way of doing it, but I just couldn't work around this. Maybe I'll share some of my thoughts on that after this proof. So let's see how we can approach this. So if such U did not exist, then we can take these U's to be the distance to the set E. So maybe actually we don't need to know that for no U this exists. So take U epsilon to be the set of points in Rn whose distance, I should actually strike the Euclidean distance, whose distance to the set E, which is infimum of distances of Z to points of E, is strictly less than epsilon for epsilon positive. So these are open sets and they contain the set. These are open and these contain the set E because it's at zero distance to them. So if they didn't work, if none of these work, if phi restricted to this U epsilon were not one-to-one, if one of them is one-to-one, we're done. So that's the claim. So proof by contradiction says, suppose that it didn't work for any epsilon positive. So we can then take a sequence of decreasing epsilon that have limit 0. And then for each epsilon, this means there is a pair. So taking a sequence as epsilon n to 0, we come up with just saying that this is not one-to-one. That means there is, for every epsilon n, there exists some xn and some yn with phi of xn equaling phi of yn. So these are, and xn not equal to yn. So this is the pair witnessing the condition that phi is not one-to-one. So that means there are at least 2 points with this equality. So notice that xn and yn, the distance of them to the set E converge to 0. We cannot guarantee that xn actually converges to some point in E, or we cannot guarantee that yn converges to some point in E, but we can move to a subsequence so that xn converges to some x for some x in the set E. So let me sketch how this we can do in a different color. These are standard things. So this is your set E. The reason you cannot pick the xn doesn't have to converge to a point is that you can have x1 here, x2 here, x3 here, x4 here, and so on. So their distance, of course, goes to 0, distance to the set E, but they don't converge. They are close to E at different locations, but we can always move to a subsequence to make that happen. And the way we can do it is, well, there is one point, because E is compact, actually there is some x1 tilde in the set E with the distance equal to the distance of x1 to, so distance of x1 to the set E is realized as a minimum, not an infimum, to some particular point on that. So it's kind of a projection. So this x3 has 1 point here, x4 has 1, and so on. Now, from these xn tilde, because this is a subsequence of the set E, has a convergent subseq to some x, which belongs to E again, because, well, it's a closed set, limit is there. And so it's then apparent that xn also converges to x, because xn minus x, triangle inequality, is less than xn to xn tilde plus xn tilde minus x, but this converges to 0. By the way, this x is born, and this converges to 0 because this is equal to the distance of xn to the set E. So very standard stuff. That's why I'm making it as a parenthetical parentheses comment. Okay, so now we know that xn, we can move to a subsequence to have this happen, but then in turn we can now do a so we have the corresponding yn sequence, further moving into a further extraction of subsequence also guarantees that yn converge to some y. So we move to a subsequence, we did it twice at least, but still we name it this way. It's standard thing in analysis. So they converge to some y in E. Now, phi of x is equal to limit of phi of xn. One of the first things everyone learns about continuity of functions. The beauty is that you can pass with limit inside the function. But remember that this is equal to limit of n to infinity. It has nothing to do with limit. At every integer n, this phi xn is equal to phi yn, and for the same reason as the first equality, this is just phi of y. So phi of x is equal to phi of y, but notice that x and y are both in E, which forces, by condition 1, so by condition 1, x must be equal to y. We know that globally on E, x is equal to y. So x could be in my picture converging to some point here, and y could be converging to something technically, but because of this last condition that phi x ends up being equal to phi of y, this shows that our sequences that we had, xn and yn's, and these converged, this forces that the convergence is actually to the same point. So there is this common point x equal to y, and this sequence yn converges to that and also does yn. And now we are at the end of the proof, because this shows, but this violates condition number 2. I can say this is the end of the proof. It's a good place now to end the proof, because it just takes a moment of thinking, because x equal to y, remember, is in the set E, and we know that there is some radius, maybe small, but anyway, some radius on which phi is supposed to be 1-to-1. But look, some of these xn yn pairs are inside this radius, and phi of this xn, huge N, is equal to phi of big y big N, while xn is not equal to yn, and this xn and yn, let's say big N and big N, are inside this ball of x and radius r x. So this contradicts the second condition. Therefore, one of these u epsilons will work. But again, that's a proof by contradiction. Now my thoughts on how we can do a more direct constructive proof is that, again, my set E doesn't have to be a line segment. It can be two-dimensional, it can be counter set, whatever. But my idea is, okay, first the covering thing, that, well, every point has some neighborhood. Let's do this one. It's better. Every point has some neighborhood on which the function is 1-to-1. And so at every x there is 1. And we can of course, the set E is contained in the union of all these balls, and we can always extract finite coverings by the definition of compactness or property of compactness, depending on how you define your compactness. That is all. We can always find just a finite bunch of centers and radii which cover the set E, and on each one phi is 1-to-1. So let's say this is one of those balls, and this is one of them, and so on. This is one of them, so you don't need anything smaller that is contained in there, and so on. Now, what I tried was to say that, okay, so this is x1, this is x2, and this is k. These are kind of the nodes And we know that f of xi is not equal to f of xj for any I equal j, right? So that's the global one-to-oneness of that. And then I was thinking about finding a lower bound on how different they can be. Like there is obviously some delta. If you have a bunch of finite numbers, there is a smaller one of them. And on the other hand, use uniform continuity to come up with some sort of condition that phi of y minus phi of this xi will be smaller than some delta 1. This is like specially chosen one. So that the way you want to prove this global one-to-oneness on my open set U will be that, okay, if you are a point here and you are another point here, so this will be close to that, so that you will have this condition. So the value of phi at this y will be very close to the value of xk here, and the value of phi here at this x will be very close to the value of x2. And now x1 and x2 are like big gap in between them, which is this condition here. And there will be this interplay between the relative sizes of this delta 1 and delta, so that if we know this is like close by delta 1 and this is close by delta 1 and this is far by delta, there's no way that phi of 1 by 1 can be equal to phi of x. Something along this line. But there are a few things, so I didn't know either to start with uniform continuity and then find these points. But then the problem is, if you first fix your finite points, say from uniform continuity, then you don't know if the balls centered at those points do form a covering or not. Maybe they become just too short and they don't end up covering your set E. And if you want a covering, then you have to assign some ball to every x. And once you extract this finite covering with finitely many center points, then these points are fixed and you lose this, you cannot use this uniform continuity to alter them, at least in an obvious way. So that was like my failed attempt at coming up with constructive direct proof. But all in all, that's maybe a good question for you to pursue. I really like this question, and I'm sure a lot can be said about this. And I'm also pretty sure this is a question written by Piotr Hajwasz, because when he has to confirm something technical for a paper, he tries to squeeze a prelim question out of it by reducing all the other details and boiling it down to the essence. And this essence here is the compactness, global one-to-oneness, injectivity on the E, and this local invertibility. You can imagine that this type of questions or constructions come up a lot in different areas of analysis. Extending a function to a larger set is, of course, a basic question, and requiring to retain properties, for example, in this case, one-to-oneness, is definitely a desirable sub-question. And this confirms that if you are one-to-one on a compact set and locally one-to-one at points from that set, then you can globally extend it to some open set. I'm sure also it's quite easy to come up with counterexamples if the set is not compact. It's kind of by artificially gluing, but not really gluing points. We have to be able to to find a counterexample. Yeah, if you find a different proof, especially a proof that is quite constructive, gives you the placement of these certain balls. Which balls do you pick so that their union covers E and we have global uniqueness? I will be very interested in that. Please do comment it below. Until another video, have a good one and thanks.